Hello friends, this video on atoms part 4 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till part 3 before going ahead with part 4. So after the failure of the Thomson's model, after a couple of years came up Rutherford's model of atom, and Rutherford's model of atom became a big hit because it was able to explain many properties. I mean, it was able to successfully explain and incorporate many things, because of which it was very easily accepted by people, right? So now, before we talk about the Rutherford's model, I will quickly introduce you to few new terminologies, that is alpha particles, beta particles, gamma rays and X-rays. Why am I introducing these? Because in the experiment which Rutherford had performed, we make use of these particles. So therefore I am giving you just a touch of what are these particles before we start with the Rutherford's model. However, we will discuss in detail about these particles in our next lesson, that is the lesson on nuclei. So here I will just give you the basic definitions of these. Now it happened in 1895 when a scientist named Roentgen showed that when electrons strike a dense metal in the cathode ray tubes, it produces rays which can cause fluorescence in the fluorescent materials placed outside the cathode ray tubes. Since he did not know the nature of this radiation, he named them as X-rays. So this is how X-rays were discovered. It is little similar to the cathode ray tube experiment, right? The same kind of apparatus, and he found that when electrons strike the dense metal, some radiations were produced. Now he did not know much about the nature of the radiation, so he named them as X-rays. So even today we call them as X-rays, right? So he found that these were not deflected by electric and magnetic fields and have a very high penetrating power through matter. And this property of X-rays, that it has got very high penetrating power, makes it very much useful in medical applications, right? You would have seen that if somebody gets a bone fractured or something like that, the doctor asks you to get an X-ray done of that body part. So what happens in an X-ray? When you do an X-ray, those radiations basically have very high penetrating power, so they can penetrate very easily inside your body, and that is how you get a scan of the internal structure of your body part, right? So X-rays have got excellent penetrating power, and they are not deflected by electric and magnetic fields. Right? They stay neutral when placed in electric field or magnetic field. Now, there are certain elements which emit radiation on their own, and this phenomenon is known as radioactivity, and such elements are called radioactive elements. Mostly these elements lie they generally have very high atomic numbers in your periodic table. So it is a property which is characteristic to those elements. It doesn't happen with all elements, right? So there are some elements they are capable of emitting radiation even if you don't do anything to them. I mean, they are just left on their own and they will emit radiation. So this phenomenon is called radioactivity, and such elements are called radioactive elements. We will talk about radioactivity in detail in our next lesson. Now, these radioactive elements generate three kinds of particles, or you can say three kinds of radiations: alpha particles, beta particles and gamma rays. So these are the three kinds of emissions that take place during radioactivity. So what are alpha particles? Alpha particles are positively charged helium nucleus. So what is your helium nucleus? With atomic number 2 and mass number 4. So alpha particles are positively charged helium nuclei. What are beta particles? They are negatively charged particles similar to electrons, right? And what are gamma rays? Gamma rays are high energy radiations like X-rays. They are neutral in nature and do not consist of particles. So that is why gamma is known as gamma rays and not as gamma particles, because they do not consist of particles. They are like radiation similar to X-rays, and they are also neutral in nature. So we will, no need to worry much about what are they and from where do these alpha particles come and all those things, because we will discuss them in detail in the next lesson. So for now, you should only know that what is alpha particle, what is beta particle, what is gamma rays, because when we discuss Rutherford's experiment, we will talk about alpha particles. Now, as regards to penetrating power, alpha particles are the least, followed by beta rays and gamma rays. So that means out of alpha, beta and gamma, gamma rays are the ones which has the highest penetrating power, right? So this was a small introduction to alpha and beta particles and gamma and X-rays. So let us now talk about Rutherford's experiment. Now, after the failure of Thomson's atomic model, Rutherford started studying the structure of atom. So he performed an experiment, and this experiment laid the milestone in determining the structure of atom. So what did he do in this experiment? He bombarded very thin gold foil with alpha particles. So this is why I introduced alpha particles, that at least now you know that okay, what are alpha particles? You can at least visualize them as positively charged helium nucleus, right? So he took some alpha particles and allowed the alpha particles to strike a very thin gold foil. So gold foil is nothing but it is a metal foil, right? How he made this arrangement, if you look at this figure, you can understand that this is your gold foil and this is a source from where your alpha particles are coming and striking this gold foil. Now, stream of high energy alpha particles from radioactive source, because you need a radioactive source. I mentioned you in the previous slide, right, that what are alpha particles? Alpha particles are emitted by certain elements which have this property of radioactivity. That is, those elements have the property that they emit radiation when they are left on their own. So we take a radioactive source and then high energy alpha particles are made to strike on the thin foil of gold metal. The thin gold foil has a circular fluorescent zinc sulfide screen around it. If you look here, this is the zinc sulfide screen. It acts as the detector. It will detect the alpha particles which are reaching the screen. So whenever alpha particles struck the screen, a tiny flash of light was produced at that point. That's because this is why a fluorescent screen is used, because so that whenever the alpha particles strike on that screen, a fluorescence is observed. So by looking at that flash of light, we can detect that okay, this alpha particle had struck at this point. Similarly, that alpha particle struck at that point. So we can understand that where exactly the alpha particles are actually striking, right? So this was the arrangement which was used by Rutherford in his famous experiment. Now, what was the result? What was observed in Rutherford's experiment? So basically, what was Rutherford's aim? His aim was to study the distribution of the number of scattered particles as a function of the angle of scattering. So what are the scattered particles in this case? If you look at the arrangement, you would see that these particles, this collimated beam which you see here, it is nothing but the beam of alpha particle. Now each of these alpha particles were getting scattered in different directions. Now this angle by which each alpha particle was getting scattered is known as the angle of scattering. So Rutherford wanted to study the distribution of these alpha particles as a function of the angle of scattering. That means, let us suppose the angle of scattering, for an angle of scattering of 30 degrees. He wanted to see how many alpha particles scattered by 30 degrees. Again, he wanted to know how many alpha particles scattered by 50 degrees, how many alpha particles scattered by 70 degrees, right? So he wanted to see, and how was he able to know that? Because whenever an alpha particle reached this detector, there was a flash. So let us suppose there was one flash, again another flash, again another flash. That means there were like total 3 flash. That means there were 3 alpha particles which reached these point. That means there are 3 alpha particles which were scattered by this angle of scattering, right? You're getting my point? So this is how this experiment helped Rutherford to actually study that how many number of alpha particles which got scattered as a function of the angle of scattering. Now, using the data which he experimentally collected, he found that if he plotted a graph taking number of scattered particles on the y-axis and scattering angle along the x-axis, he found a graph of this sort. That means as the angle of scattering increased, the number of alpha particles decreased. That means there were very few alpha particles which were scattered by a greater angle. Right? So when will be the scattering angle large? Scattering angle large. Scattering angle large means, what does it mean? Let us suppose if this is my alpha particle. This is my alpha particle, right? This alpha particle approaches this object. Now, if this alpha particle gets scattered by a very large angle, that means this alpha particle is highly repelled by this object, because if the alpha particle would have been attracted by the object, it would have not scattered, it would have got attracted towards the object and gone like this. Now, if an alpha particle is getting scattered by a very large angle, that means that alpha particle is experiencing a strong repulsive force. So that means for large theta, so somewhere around this portion, when theta is large, that means the alpha particle experiences a repulsive force. So what does this graph tells us? This means repulsive force is more. Now from this graph we see that for large theta, the number of alpha particles is very small. That means this implies that very less number of alpha particles are repelled, right? Because there are very less number of alpha particles which are scattered by large theta. Now since there are very less number, therefore there are very less number of alpha particles which are repelled, right? So what does this mean? This means that the dense part inside the atom is very small. That means the atom is not dense everywhere, as was told by Thomson. What did Thomson tell? Thomson's model told that the entire atom consists of positive charge uniformly distributed everywhere, right? So that means according to Thomson, the atom as a whole was dense. But from Rutherford's experiment, it was seen that since very less number of alpha particles are getting repelled, that means the dense part inside the atom is located or is localized into a small region, and this dense part was nothing but the nucleus, because the alpha particles are positively charged. So alpha particles are getting repelled by a positive charge, can get repelled by a positive charge. So that means this dense part was positively charged and this dense part was known as nucleus. So from this it was discovered that nucleus is only a small portion of the entire atom. So that is how I compared the size of nucleus with the atom in the first screen, right? That where I told that if a cricket ball is your nucleus, then the radius of the atom is somewhere around 5 kilometers. Right? So from this you can see that there were so many alpha particles which were striking the target, but only very few of them got repelled. That means there is only a very small positively charged dense part inside the atom which is known as nucleus. So this nucleus is the only portion which is repelling the incoming alpha particles. Right? So therefore it was concluded that most of the mass of the atom is concentrated at the nucleus, right? So what is the remaining portion of the atom? The remaining portion is empty, and the remaining portion consists of the electrons which are orbiting around the nucleus. So now the question is, how are the electrons arranged, or how is the electron distributed in an atom? So from this part you understood that how Rutherford concluded that nucleus consists of most of the mass of the atom is at the nucleus, and also he concluded that nucleus is only a small portion of the atom. The rest of the atom is empty. The rest of the atom is not dense. It consists of electrons moving around the nucleus. Right? Okay. So from Rutherford's experiment and his observations, what did he conclude? So one point I discussed in the previous slide, right? That since it was found that very few alpha particles got repelled, so it was concluded that that means the positive charge inside the atom is localized in a very small region, and that is why it repelled a very few alpha particles. So what was this force of repulsion between alpha particle and the nucleus? The force of repulsion between the alpha particle and the nucleus was given by the Coulomb's force, that is 1 by 4 pi epsilon naught into charge on alpha particle, that is 2e, because it is helium nucleus. Helium nucleus has 2 electrons. Therefore, the charge on the alpha particles will be 2 into charge of an electron into the charge of the nucleus. So, how many electrons are there in the nucleus? Number of electrons in a nucleus is nothing but the atomic number, that is represented by Z. So this would be the charge on the nucleus divided by r square, where r is the distance between the alpha particle and the nucleus. So the magnitude and direction of this force of repulsion between the alpha particle and the nucleus changes as the alpha particles comes nearer to the nucleus, right? Okay, so now what did Rutherford finally concluded? So final conclusion given by Rutherford was that since most of the alpha particles passed through the foil undeflected, as I mentioned, only few alpha particles got deflected. Rest of them, they moved through the foil undeflected. So what did this tell? From this he concluded that most of the space in an atom is empty. Right, that is why it did not get deflected, because there was no obstruction inside the atom. So that means most of the space in the atom is empty. His next observation was that a few positively charged alpha particles were deflected. So this we discussed in the previous slide. So for this he concluded that positive charge is concentrated in a very small volume inside the atom that repelled and deflected the positively charged alpha particle, right? And this small positive charge, which was concentrated in a very small volume inside the atom, constituted the nucleus, right? Okay. What else? Calculations by Rutherford showed that the volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. The best example, the comparison of the cricket ball, right? The radius of the atom is about 10 to the power minus 10 meters, whereas that of the nucleus is 10 to the power minus 15 meters. So if you see, there's a difference of 10 to the power 5, right? So it's a huge difference between the radius of the nucleus and the radius of the atom. Right, so these were some of the important conclusions of Rutherford's model of atom, and this laid the basic of how we see the structure of an atom today, because these things which Rutherford found with the help of his gold foil experiment turned out to be extremely useful for later studies. So Rutherford's model of atom was finally defined somewhat like this. The positive charge and most of the mass of the atom was densely concentrated in extremely small region. This very small portion of the atom was called nucleus by Rutherford. So Rutherford was the one who, in a way you can say that he was the one who discovered the nucleus. I mean, he was the one who told that, okay, inside the atom you have the positive charge in a small region, that region is nucleus, right? He was the one who told that the nucleus is surrounded by electrons that move around the nucleus with a very high speed in circular paths called orbits. Because he experimentally found that only small region was dense, and that was nucleus. Rest of the region was all empty. But since the atom was electrically neutral as a whole, so that means if you have a positive charge, there has to be some negative charge, and those negative charges were electrons. So he told that the electrons were moving in circular paths in that empty space, and these circular paths are known as orbits. So Rutherford's model of atom resembles the solar system in which the nucleus plays the role of the sun and the electrons that of revolving planets. Like how in our solar system we have the sun and all the planets revolving around the sun. Similarly, you have the nucleus and all the electrons revolving around the nucleus. Right? So this was Rutherford's model. He told that the electrons and the nucleus was held together by electrostatic forces of attraction. Right? So Rutherford's model of atom was very similar, or it was analogous to our solar system. Right? So many times, since Rutherford was the one who spoke about the existence of the nucleus for the first time, therefore Rutherford's model of atom is often known as the Rutherford's nuclear model of atom. Because before Rutherford, it was Thomson who did not talk about nucleus at all. He just told that positive charge is there everywhere inside the nucleus. So according to him, the atom is dense everywhere. Again, prior to him was Dalton, who even did not mention anything about the constituent of the atom. He just told that atom cannot be divided further. Right? So it was Rutherford who came up with a very important conclusion. Right?
Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.